welcome to this presentation on fast likelihood computation for attentional drift diffusion models and beyond. This is joint work with my collaborator Sicheng Liu from the Applied Math Department at Brown University, and we are guided by Professor Matthew Harrison and Professor Michael Frank from Brown University as well. Let me start without explaining anything in detail, given the audience of this conference, with our beloved drift diffusion model, which is a very widely applied model, and it attempts to model reaction times and choices jointly using very few but interpretable parameters that can be nicely linked to latent aspects of the cognitive process that may be involved in deciding over the dominant direction of motions in a dot motion task very canonically. But it is really a model that is applied across a large variety of stimulus modalities, including such decisions as which donut of two particular donuts do I prefer. Now, there are many variations of interest of this model, and those have been sufficiently motivated in the theoretical literature. However, until recently, empirical data analysis has put an outsized focus on the basic DDM. And why would this be? In large part, this is at least our take, this is because of analytical convenience. The likelihood computations for the basic drift diffusion model are much faster and easier to conduct than for some of these variations. And that also led to an outsized software support for the basic DDM as compared to a dearth of software support for to support inference for any of the variations of drift diffusion models. Now, a recent boost in methods and jointly software support has leveled the playing field a bit between variations of the drift diffusion model and the basic drift diffusion model. And that's in large part driven by the search of the field of simulation-based inference, which starts from the assumption of only being able to simulate from a process and intersects now with deep learning to then learn networks that either target the posterior for a given inference problem or target the likelihood of a generative process. Moreover, specifically in the domain of these diffusion models or sequential sampling models, there has been a emergence of a toolbox PyDDM, which is based on the computations of which are based on Fokker-Planck equations. But PyDDM, which in the context of this talk is actually going to be our main reference point for comparison, has had a great impact on the ability for researchers to fit complex variations of these drift diffusion models. Now, well, one could say, okay, so now we have all the software support available for a much more general drift diffusion processes. Now, are we done, basically? Is it now down to us just coming up with fancy models and taking the computational modeling from there because we have all the support now? Well, it's not exactly like this, because there's a class of models that still remain largely unaffected by those developments. And one canonical example for this class of models would be the attentional drift diffusion model, which has as its distinguishing factor the fact that it's based on a fixed covariate of fixation trajectories, which changes for every single trial and has to be conditioned on top of the underlying parameter drivers of the process, or the underlying parameters that drive the sequential sampling process. So in math, maybe, or in notation on the right-hand side, we can see that the difference here between something like the attentional drift diffusion model and, let's say, our standard version of applying Bayes' rule is that instead of just having the parameters of the process, theta, we now have the parameters of the process and fixed covariates, which in this case would be, for example, saccade times. For trial I have saccade times 1 to m, a varying number also of saccade times across trials, and varying saccade durations, of course. Now, for the deep learning approaches, this creates some trouble because it makes the training problem much more unwieldy. It creates an inflation of the input dimensions, And therefore, it's going to create an inflation of the number of training examples necessary to learn such a, to learn either likelihood or the posterior for such a model. And for these Fokker-Planck-based methods, which something like the otherwise very successful PyDDM toolbox is based on, it creates the following problem. So these Fokker-Planck equations ultimately boil down to grid computations, where for a given set of parameters, I'm going to be able to compute a grid from which I can derive likelihoods across time. And then once I have those likelihoods, I can evaluate those for many trials at once very quickly. However, the grid computation itself is slightly expensive. And this is great if I can reuse a grid from many trials. However, it's not amazing if every trial is essentially its own condition. So we have to recompute the grid for every trial. So this leaves us with the following desiderata. So we would like to have an approach that focuses on single trial computations. So it does only the minimum necessary to get a likelihood for a single trial, and then is flexible / modular for trial-wise fixed covariates, which in our case here, for our running example, the attentional DDM, would be different types of fixation trajectories. So I'll hand it over to my collaborator, Xiqing Liu, to explain our proposed method in the following.
So, hi, I'm Sicheng Liu, and I'll take it from here to continue introduce our proposed method for fast and accurate likelihood computation for attentional drift diffusion models. So as we discussed before, what's inefficient about current existing method? If you want to numerically solve the Fokker-Planck equation using finite difference method, you need to evaluate the solution of the PD on a fine spatial temporal grid, and the approximation error of that likelihood goes smaller as the grid size goes smaller. This is only efficient if you only have to solve the PD once to get the likelihood of all trials. However, for ADDM type of model, each trial has the Saccard time as its own condition, so that we have to solve different Fokker-Planck equations for each trial, and that becomes computationally expensive. We hence propose an alternative method. We observe that the ADDM actually has a strong piecewise characteristics. For each trial, we actually can get a temporal grid of much larger size by dividing each trial as Saccard time, so that each divided time stage has constant drift, which can be interpreted as constant attention, and that's much easier to deal with. This is an illustration with two stages. For the first stage, with all the parameters, the boundary, the initial point, the drift known, we can get the exit position distribution at the first Saccard time, as shown here by this green curve. We can also get the density, first exit time density on the upper boundary and lower boundary. If you don't have Saccards, the drift is constant. Like you can just get the exit likelihood by these analytical formulas. But if you have at least one Saccard time, you have at least the second stage, you can use the exit position distribution here from the first stage at the initial starting point distribution from the second stage. And then all the likelihoods, the upper boundary, lower boundary, also the vertical boundary, the likelihood can be obtained by taking the expectation of the same formulas with respect to this initial point distribution, which is inherited from the first stage. With this idea, we can actually stitch any number of stages together and calculate the first passage time likelihood by a sequential integration, as the stages for a given trial are provided by observed fixation trajectory. Another thing was mentioning that because we know the Saccard time in advance, like at each stage, we use a higher order Gauss-Lagrange quadrature for the numerical integration. Those integration points are fixed, so it can be pre-computed at the Saccard time, so that everything can support automatic differentiation. Here we show some numerical examples. The first example is a drift diffusion model with piecewise constant drift. Here, it is different to the attentional drift diffusion model in the sense that all trials share the same piecewise constant drift, and the boundary is a linear collapsing boundary. In this figure, we can show that despite the likelihood of this process is actually very complicated, we are still able to capture the shape of this complicated likelihood as it fits quite well with the Monte Carlo estimates, as we show in the histogram. In the second example, we want to stretch our method to its limit. We consider approximate drift diffusion model with some general nonlinear drift and boundaries. Here we show an example with a Weibull CDF boundary as long as a sine wave drift. We can approximate these curved boundary by its linear interpolation. If you use interpolation points of large numbers, so that the approximation becomes close to the original one, as we show in this figure, we are still able to compute the likelihood quite accurately. The last example is a parameter recovery for attentional drift diffusion model. In this example, each trial doesn't share the same saccades. They have their individual saccades simulated from some stochastic processes, and we recover the parameter mu1, mu2, a, b, and x0. A and b are the intercept and slope for the linear collapsing boundaries, and we compute the likelihood at the dataset consists of 50,000 trials and perform maximum likelihood estimation, and we were able to get that our estimate parameter is also quite close from the true one. It indicates that we were able to do accurate parameter recovery. The whole optimization process takes around 1 minute, so it's also very fast. So for the advantage of our method, we only need to compute the likelihood of a single reaction time choice pair. So we are very fast in the sense that we minimize the computation we needed for each trial. Also, we use highly accurate analytical formulas in time, and in the sense that up to translation error, we are almost exact. And we use high order numerical quadrature for integration in space. You can use arbitrary high order you can get so that the spatial integration can be as accurate as you want. In contrast, Fokker-Planck method, if you use Krag-Nicholson as a finite difference discretization, is at most second order in both space and time. So here we show the timing test for compute the likelihood of an attentional drift diffusion model of a dataset consider 50,000 trials. The serial performance of our method outperforms the Fokker-Planck method by several orders of magnitude, and also our method can be parallelized by OpenMP, and we also get a good linear scaling of our parallelization. So our method is very fast and suitable for broadcast model with trial-specific covariates. However, it's not directly applicable for model with state dependency. For example, the Ornstein-Uhlenberg process shown here. Future works of our work can include. So first, as mentioned before, our algorithm is end-to-end differentiable. So if written, we plan to written in JAX to enable automatic differentiation, so that gradient-based optimization method can be used for maximum likelihood, and we can also explore Hamiltonian Monte Carlo for Bayesian inference. We are also plan to exploring putting it on GPU for better parallelization performance. We are also working on combining this idea to the likelihood approximation neural network paradigm to get a statewise lens to generalize to even broader class of generative models. Finally, everything about this work will be integrated with the ICCM toolbox to facilitate its use to this community. This is the end of my presentation, and this is our mentor, Matt Harrison, and Michael Frank, and this is the reference of our work. Thank you.